thing you'll find. It certainly flies a lot different than the airplanes you've been working with before. When you get in the front seat, even with an instructor pilot in the rear, you must have full knowledge of the aircraft, its systems, emergency procedures, its capabilities, and limitations. It can pay off with your life sometime.
How fast does the B-47 really go?
What's the scoop on altitude? Does the swept-back wing really stall out easier? What's the range?
Wait a minute, fellas. To fly the B-47 safely, you must learn it thoroughly. Believe me, you can't learn it overnight. So absorb all the training you can get. Absorb it thoroughly. Just sit down, fellas. I don't want to scare you. There's nothing mysterious about the B-47. It's a good plane, a safe plane, provided you know what you're doing at all times. It has some new features you're probably not familiar with. Features that will present you with some new problems. To let you meet the B-47 and get you familiar with some of these differences, well, let's go back a little in time. As you all know, in the evolution of weapons, instruments of offense and defense are continuously competing for superiority. You build a tank, then you develop an anti-tank gun. You build a bomber for offense, then a better fighter for defense. If it happens to be a jet fighter, then the logical next move is to produce a jet bomber, but quick. Well, that was about the situation in June, I think it was. June of 1943. The Nazis were putting jet fighters into combat, so our need for a jet bomber was clear. An aircraft to be built around an engine. It would have to have speed, more speed than was ever thought possible for a bomber before. It needed altitude. The higher, the better. It had to have range. That was a sore spot, too. For the first time in any set of requirements, ease of maintenance was a priority consideration. Designers and engineers all over the country analyzed the requirements in terms of the data available in 1943. They worked with slipsticks, drafting boards, wind tunnels. It was common knowledge that the piston pounders of the day attained their optimum range and performance at a moderate speed and in the lower altitudes. One of the most discouraging features of the jet engine was its staggering fuel consumption. This generated some ulcer-provoking problems of range and extremely high gross weights. It was known that a jet engine would deliver its best performance near its maximum speed and at very high altitudes. It would also use less fuel operating under these conditions. In the first model, 4 jet engines were mounted on a thin version of a conventional straight wing. But a straight wing just didn't have enough speed advantage. To find a high-speed wing, the wind tunnel did a free beer business with all kinds of problems. Early data favored a clean wing, so the engines were fitted into the fuselage along with the fuel tanks. The wings still couldn't achieve enough speed. About this time, the Allied armies had conquered Hitler's Europe. Captured Nazi research data revealed that the Germans had developed a radical wing design, the swept wing. The plans indicated that the wing could withstand extremely high speeds. Wind tunnel tests confirmed this fact, but it also revealed some sobering problems of sweepback. By increasing the angle of sweep, you can increase the critical speed of the airfoil. But as you increase the angle of sweep, you decrease the span. Since the range of any airfoil is a function of span, they had to compromise to get the maximum of both speed and range. The wind tunnel and slide rule discovered problems of lateral control at the lower air speeds caused by the tendency of the outer portion of the swept wing to stall first. So the problems of lateral control were reduced by designing large aileron and flap areas. To keep the wing clean, the engines were kept in the fuselage along with the fuel. However, with this arrangement, an engine fire could be disastrous. The insulation required to protect the fuselage and fuel was impractical. The engines were too inaccessible for maintenance, so they were fitted below the wing. When the outboard engine nacelle was added, the problems of lateral control were further reduced. To keep the wing clean and thin, a variety of landing gear arrangements were tried. As the design progressed, the tandem gear came into the picture, retracting the main gear along the center line of the fuselage. This looked like the answer. In order to accept the high load factors imposed upon it during all flight conditions, the thin wing had to be extremely flexible. So the wing was designed to move through a 17-foot arc at the tip. The wind tunnel experiments on this flexible model were severe. The tunnel's wind currents worked the model over in every possible attitude of flight, subjecting it to every speed condition from the slowest up to disintegration. Here, engineers discovered some disadvantages of the swept wing, like additional weight for wing structure, tough problems of lateral control at low air speeds, longer takeoff and landing rolls due to the necessary high speeds. But the speed potential of a swept wing was worth accepting the disadvantages. By November 1945, the present configuration and arrangement was pretty well firmed up, and Boeing began to build 2 prototypes incorporating a 35-degree angle of sweep in the wing. On December 17, 1947, 44 years to the day after the Wright brothers made aviation an airborne reality at Kitty Hawk Beach, the jet bomber idea went on trial. The Stratojet was all set to try its wings, and they worked. A bomber designed to have a margin of performance over all other aircraft. An offensive flying machine designed to aggravate the interception problem of fighters and frustrate every possible defense for years to come. It didn't take long to realize that we had the offensive weapon we ordered, that the Air Force had become landlord of the fastest bomber in the world. The first airplanes that rolled off the assembly lines at Wichita were subjected to intensive tests by a composite group of Air Force specialists. They learned the airplane the hard way during extensive, sometimes merciless operational suitability tests. A lot of plain old hard work to learn if it was a safe airplane, how to maintain it, what supplies, facilities, and personnel were needed. The test program paid off in a big way for the Air Force. Sizable dividends in knowledge and experience. For instance, they learned some very important facts about landing. Don't land the front gear first. If you do, the rear gear is forced down and the airplane is flying again at a dangerous angle of attack. Under normal conditions, don't pull the drag chute in the air, because it will decelerate the plane into a stall condition and may prove dangerous if the plane is too high. The chute can correct for many things in a landing, such as drifting in a crosswind, bounce on landing, or too fast an approach. However, it should not be used as a pilot error corrective measure. With their test, the men of the project were able to discover many of the shortcomings and limitations of the B-47 early, so that the manufacturer could correct for them and minimize the modifications necessary on the mass production model. Here's a bird that will perform successfully if you, the people who will make the decisions at the controls, will only spend the effort to learn and adapt to a new set of flying problems and characteristics. That's your mission. When you've completed that mission, you'll be B-47 crew members yourselves. You know, the B-47 is a pretty outstanding airplane on the ground, too. It's covered with maintenance access panels to help the men behind the flying crews to do their jobs in less time than previous bombers required. Packing that handy drag chute is no problem either. It's almost as easy as putting dirty clothes in a barracks bag. Your B-47 needs an amazing volume of fuel for a long-range operation. In a jet airplane, fuel is a critical item. Every phase of your mission plan, range, endurance, as well as takeoffs and landings, gives fuel quantity a high priority. So your cockpit fuel gauges read in pounds and not in gallons. This lets you know at a glance the weight of the fuel available in your tanks, and what's more important, the amount of power you have to complete your mission. Now that you're here to become B-47 crew members, it won't be long until you find out for yourselves that operating a B-47 is an elaborate and serious enterprise. So you plan seriously for every detail of the mission. Just keep in mind that with the high speed and limited fuel, your mission plan for this aircraft has to be right the first time. Now, actually, your B-47 mission plan is less complicated, but a lot more critical than mission plans for the aircraft you have been flying. Anyone who has flown the airplane on a few missions will tell you that you can get the complete advantages out of every feature of the B-47 if you will plan every phase of its operation. In the air, you know you're going to be your own flight engineer. Even so, planning your missions in a B-47 is really simpler than with previous bombers. You don't have the old string of problems like cowl flaps, mixture controls, manifold pressure, and so forth. But you do have some new problems to consider with the airplane. And you'll have the solution right with you, as standard an item as your oxygen mask and crash helmet. If you're serious with your mission plan, it's like a guarantee in writing that you'll be getting the maximum performance out of the airplane. There's only one altitude for the best range. Since it's based largely on gross weight, your mission plan figures the fuel you're going to use for taxi and takeoff, and during climb to altitude. In order to maintain your optimum altitude at all times, you allow for the rapid decrease in gross weight by use of a climbing flight plan. But with a serious approach to your mission planning, you can pretty accurately estimate all the variables and get the maximum performance from every feature of the airplane. To guarantee that you'll be around to collect some of those fogies you're building up, don't be in too big a hurry when you get out to the airplane. It's never a bad idea to start things off discussing the status of the airplane with the crew chief. He won't be around if you need him upstairs. Flying this brute makes large demands on all the plane driving experience you've ever logged. So don't slough off anything on that exterior inspection. The three people who will make this piece of machinery a powerful tactical weapon will spend their flying time in an inner pressurized capsule, set high in the forward section. The cockpit checklist is designed to save time and fuel on the ground, because every minute the engine runs on the ground cuts a big chunk off your flying range. To complete the cockpit check requires interphone conversation between the three crew members and the man on the ground.
Let's have an interphone check. Co-pilot ready. Navigator all set. Ground crew ready. Ready to check surface control. Boost off. Right aileron up. Left aileron down.
When you're flying at high speeds, the air exerts an extremely heavy force on all the control surfaces. In this airplane, you have the option of greatly reducing the effort involved by cutting in the hydraulic power control system, the boost, to all the control surfaces. The newness of the airplane, with its new pattern of flying characteristics, required a new kind of control surface, the flaperon. They're practically identical to the flaps in every way, but their function is unique. They're available to minimize and perhaps eliminate a potentially serious problem of maneuvering the B-47. The basic problem is simply this. On a swept wing, the center of lift tends always to shift outboard. At low air speeds, in a stall for example, The still air on the top surface of the wing moves toward the wing tips and literally piles up. With the surface power control on, the flaperon, once extended, will rotate upward when the aileron on its side goes up over 5 degrees. The flaperon actually spills the still air before it can pile up and create a serious lateral control problem at low air speeds. You don't have to allow any time for engine warm-up. Once these jets are fired up, they're ready to fly. They do have a mean streak, so clear the danger areas well ahead and behind the engines and go to it.
Ready to start number 4. Co-pilot ready. We're on clear and ready. Energizing number 4. Start on 4.
Don't be in too big a hurry to get them all going. There's no easier way to wash out a jet engine than poor starting technique. Taxi out with 2 engines. The minimum thrust to start a ground roll and still hold down fuel consumption. The problem of directional control while taxiing this airplane is different too. Neither differential braking nor differential engine thrust will steer a tandem gear. So the forward gear is steerable hydraulically with the rudder pedals. The ratio of steering rotation is selected by the pilot. 120 degrees swing for towing, 120 degrees for taxiing, and 12 degrees for takeoff and landing. Once you're lined up on the runway, all you need is a final check and power for the takeoff roll. The takeoff attitude of the plane is fixed. You always take off and land with full flaps. In a crosswind, you'll use some aileron to keep from listing. The flap rods will be in there pitching too. You can't pull it off. When it's good and ready, the plane will fly off by itself. You never have to milk up the flaps. If you reach your mushing or sinking point before you have sufficient flap-up speed, the flaps will stop automatically until safe speed is achieved. Because of the inefficiency of jet engines at low air speeds, the plane requires a considerably longer ground roll. The airplane was designed to have a maximum gross takeoff weight of over 180,000 pounds. Gross weight, runway elevation, and outside air temperature have a large effect on takeoff distance. So, under certain conditions, the B-47 needs some sort of assistance for takeoff. In your mission plan, you determined your optimum speed for firing the units. When you're ready, they fire simultaneously by a single switch.
Reno.
Your fuel consumption can be 3 times as great at sea level as at high altitude. Since the only way to lean out is to go up, climb to optimum cruise altitude as quickly as possible. Of course, the best indicated climb speed will decrease with altitude. So take it up at the airspeed you figured to be best in your mission plan. From here on, there are only 2 things that will affect range: your throttle and your altitude. At altitude, you'll get the maximum range and performance out of the airplane by following the gradual climbing flight path you sketched in your mission plan. So after leveling off, stay at a constant Mach number and a pretty constant power setting. There's something else you're going to appreciate about this airplane. Danger from engine fire is greatly minimized. For one thing, all the fuel aboard is in the fuselage. So if you ever have a fire, all you need to do is cut off the flow of the fuel to the engine and isolate the engine with the fire button, and the fire should go out. No CO2 required. In a B-47, you're flying the fastest and safest means of round-trip transportation from a forward base to any target in the world. Speed and altitude are your principal defense. You have a comfortable margin on almost everything else that flies. Many times on your missions, you're going to want it to operate as close to the speed of sound as possible. Practical and safe. There's an interesting point about that. One I didn't know about before anyway. It seems a curious old German scientist named Mach discovered that the speed of sound varies with the temperature of still air. Now, generally speaking, as you go up into the higher altitudes, the air gets colder and the speed of sound decreases. In the new group of expressions you'll be picking up around here, the speed of sound is known as Mach 1. Your B-47 is built to safely approach a certain percentage of Mach 1. Knowing how to operate within your allowable percentage is going to help you become one of those ripe old pilots someday. The percentage you are allowed is about as critical as your paycheck. As a matter of fact, your critical speed is called your critical Mach number. The airplane has a purposeful instrument called a Mach meter, which calibrates your true airspeed in terms of Mach. It saves a lot of mileage on your slide rule and lets you know at any time the ratio between the speed you're flying and the speed of sound. For example, at 0.75 Mach, you're moving along at 75% of the speed of sound at your altitude. B-47 stall characteristics are good. They do have one feature, though, that you'd better dig in and learn all about. An aerodynamic effect called buffeting. On the B-47, it amounts to a vibration all over the airplane that can build up to a violent and dangerous shaking under certain conditions. It starts when the smooth airflow across the airfoils begins to separate in any stall. As the flow separation increases, drag increases rapidly, and the airplane begins to buffet. If it gets to an advanced stage, the controls become ineffective. In a high-speed stall, advanced buffeting means that you're on the edge of serious trouble because you're approaching your critical Mach number. All airplanes have a critical Mach number, but very few have the power to reach such a high speed. But the B-47 has more than enough power to reach its critical Mach. To get the most efficient use of the airplane's capabilities, you have to fly at a speed that is very close to your critical Mach number. You can slip the B-47 right up next to its critical Mach limits and either cruise there safely or clobber yourself. It's your own personal choice to make. If you ever do get in trouble, here's what's happening. As a multi-engine jet jockey, you have to fly inside a couple of rigid speed curves. On one side, your stall speed increases with altitude. On the other, high-speed buffeting speed decreases with altitude. The higher you go, the narrower the operational range gets between a high and low-speed stall in level flight. It's possible to reach an altitude where you will stall out in level flight. If you do get up against your critical Mach number and into buffeting, it takes time to back off. To slow down in a reciprocating airplane, normally all you had to do was either decrease power or climb. But in a jet airplane, to minimize the possibility of flameout, your minimum RPM automatically gets higher with altitude. So at the higher altitudes, even with the throttles back to idle, you will be cruising at a very high RPM. To climb would only put you farther into the corner. Because of pilot fatigue on the return from a mission or pilot error anytime, you can lose track of Mach number and the other variables until you have too much of all of them on your hands. For safety reasons, you have to keep an eye on the key instruments all the time. Of course, the best idea is to realize well in advance that you are approaching your critical Mach or stall speed and plan ahead. Letdown brings up another new group of special problems for solution. In order to avoid the enormous fuel consumption of low altitudes, you'll maintain your cruising altitude much closer to your destination point than in a prop-driven aircraft, practically over your home base. The main landing gear has over twice the total drag of the airplane. They act as your dive brakes. The rear gear and outriggers can be lowered at very high indicated airspeeds. The front gear is lowered as soon as the aircraft has decreased speed to below 174 knots. Just hold the best indicated airspeed you estimated in your mission plan and come on down. As you approach your landing base, you spend a minute or two checking your fuel and computing your gross weight at the landing point. Once you've figured it out, you can determine your safest approach and touchdown speed. Many times you'll enter the pattern with full flaps and start slowing down as early as the downwind leg. Slowing the B-47 down, even in a power-off condition, is a time-consuming operation because there's no prop drag to help you, and the airplane is so clean. We have some pretty strong reasons for a well-calculated approach and landing.
Remember this. Every 5 knots of excess airspeed costs you 1,000 feet of runway. Once you're committed to a landing, don't hold the airplane off. For the best landings, you let the 2 main gears touch simultaneously. But it's still a good, safe landing if the rear gear touches first and the forward unit settles easily on the runway. In a crosswind during both takeoff and landing rolls, you can hold the wings level with the aileron. Jet engines produce a sizable thrust, even at idle RPM setting. It takes about twice as long to go from idle to 100% as from 50% to 100%. So maintain about 50% RPM until you're certain of landing or going around. Remember, there's no lift across the wing from propellers. So if it's necessary to refuse a landing, decide it as early as possible and open the thrust. Since approach speeds are very close to actual touchdown speeds, fly well ahead of the airplane, all the time. The jet engine slow reaction time doesn't allow you the privilege of last-minute decisions. Plan ahead. Remember, if your decision to go around is too late, you'll have to allow the plane to touch the runway after you apply full throttle. Cut your ground roll almost in half by releasing the drag chute as you contact the runway. It's made a lot of good landings and safe landings out of potentially bad or dangerous ones. Remember, the chute can correct many errors like bounce, deviation in a crosswind, or a landing that's too fast. It's most effective at higher speeds, so get it out as soon as you can. If necessary, anti-skid brakes and chute can be used simultaneously. However, it saves a good deal of tire and brake wear if you wait until the plane has decelerated a good deal before applying the brakes.
In the evolution of weapons, instruments of offense and defense are competing continuously for superiority. The arsenal of flying machines, the advantage of speed has formerly been the exclusive province of fighters. B-47 is the new concept, the new advantage for round-trip bombing missions. For a long time to come, the B-47 will be the best answer, possibly the best solution, for the largest problems of delivering bombs to targets and getting flight crews home safely. Your greatest asset is speed. And you'll have enough of it at your fingertips to make interception by present-day fighters extremely difficult. The B-47 has a way of flying all its own. It takes a little time and a lot of hard work to master it. But if you honestly like to fly, it's worth it. It's really the best.